Hi guys, today's webinar is going to be a GCSE Physics webinar on energy transfers. So if you don't know me already, I'm kind of hosting all the GCSE Physics webinars. My name is Preshayla and I study at Loughborough University. It's my fourth year as a tutor. So what we're going to be covering today is learning about the behaviour of energy and that it can be wasted. We're going to go through the equation for efficiency, understand ways in which we can reduce waste energy, understand how energy can be lost in a house and the ways that we can reduce this loss, define thermal conductivity, and understand the required practical. So we do have quite a lot to get through today, but we will go through some example questions and we will always have time for your questions at the end. As always, this session is an hour long. Myself and Bola are here to answer any questions that you have either about the lesson itself or about my tutor. So do just put them in the Q&A function or just in the chat. So yeah, let's get started. Okay, so I'm going to start off with a really quick summary of what we covered yesterday in the webinar. So all to do with energy changes. So we were talking about heating materials and the energy changes that can be involved in that and how it actually works. So with the molecules getting faster, getting more kinetic energy and that coming out as thermal energy. We then looked at the equation for calculating thermal energy, which if you remember was the change in thermal energy equals mass times specific heat capacity times the change in temperature, or E equals mc delta theta. We then went on to talk a little bit more about specific heat capacity and what it actually means, as well as looking at two new equations for power. And the fact that they can be interchangeable with each other. So work done and energy transfer can be interchangeable. And then we went through the required practical on specific heat capacity. So if you do want to know more in depth about those webinars, if you did miss it, it's always on YouTube. Okay, so the behaviour of energy. We've already talked about the fact that energy can be transferred usefully, stored, or dissipated as waste energy, but it cannot be created or destroyed. So we need to know about three different types of systems and how energy behaves in those systems. So the three types of systems that we have is open, closed, and isolated. So as you can see in the little figure here, we have an open system, a closed system, and an isolated system. The open one is an open cup, energy can leave and heat can be lost to the surrounding. So that could be a cup of coffee and the heat that is in the coffee from the boiling water leaves and heats up the surrounding around the cup. So an open system loses energy very easily. A closed system keeps all of that energy in. Okay, it might lose some to the walls of the bottle, but it keeps all that energy in. An isolated system doesn't let any energy out or any energy in. Okay, so it's keeping it warm, it's a flask, it's keeping all that energy in. The way that we like to describe it as tutors and teachers is the energy that was created in the Big Bang is all going to still be there at the end of time, okay, because there is no change in energy. Energy can't be created or destroyed. It's always just being transferred from one form to another. It's kind of a weird concept to get your head around. Okay, so we have this thing called wasteful energy. When we talk about wasteful energy, what we really mean is energy that is not doing the thing that we want it to do. So, for example, in a microwave, you want it to heat up your food. That's the only purpose. You don't care about anything else. You just want your food hot. Any other function that that microwave does is useless to you. Okay, so for example, the sound, your microwave might make a sound when you're heating food up. That's not useful to us, right? The sound that we hear when it's heating is not useful. The ping at the end is useful, but the sound is not useful. And that's energy being wasted. Okay, so no energy transfer is going to be 100% efficient. It's inevitable. We're always going to have wasted energy. In a light bulb, we only want it to light up, but it's inevitable that the light is going to get hot. Okay, the lamp is going to get hot no matter what we do. We can try and increase this efficiency, and we can get it as close as we can try and get it as close to 100% as possible, but we're never going to reach 100%. Okay, that's just the way energy works. We're always going to lose some. Okay, so we need to think about energy transfers and where the waste goes. Okay, so for these 5 scenarios, I want us to think about what the energy transfers are and where the waste energy goes. So for the first scenario, we have fuel in a car making a car move. Well, the energy transfers involved in that is chemical energy in the fuel going to kinetic energy to make the car move. Okay, so that's the energy transfers that we have, but there's going to be some waste energy. So where does that waste energy go? And what is the waste energy? Well, in a car, because fuel is turning into motion, we're going to lose some energy as heat, and engines can get hot. They can get really, really hot. And actually, most of the energy that the fuel creates is just getting lost to the heat of the motor. Okay, so yes, some of it is going to what we want. It's going to make the car move, but actually quite a lot of it is wasted as heat energy. And it's heating up the motor. That's obviously got no use to us and actually can be quite dangerous to us. Same thing with a light shining on a solar panel. So we have light energy coming from the sun, which goes to electrical energy to power our houses. However, some of that light energy is just going to be wasted. It's going to heat up, it's going to light up the solar panel. That's not helpful to us. Okay. Charging our phone, you're going to charge your phone, let's say up to 100%. Not all of that battery that you have is going to go to functioning the phone. Let's say you charge your phone for 4 hours, your phone might only last for 1. Okay, so not all of that battery goes into functioning the phone. Some of the energy from when you charged your phone gets wasted as heat. So you might feel your phone starts to get hot when you charge it, it's wasted. Lighting a fire in a dark, warm room. Okay, so if we were to light a fire in a dark, warm room, the purpose is clearly to light up the room, not to heat the room. Okay, so the fire, its purpose is lighting up the room. The wasted energy would be the heat. Lighting a fire in a bright, cold room, well, we want the fire in this case to warm up the room. It's already light, that's not what the fire is being used for. We want the fire to warm up the room. So in that case, the function is to heat up the room and the wasted energy is the light. So do remember that, yes, we have wasteful energy and in most cases it is going to be heat, but sometimes we need to go back to what really the function of this appliance, of this application is, to really think about what the wasteful energy is. So always think about the function, what we want to get out of the appliance before we think about waste energy. Okay, so that leads us on nicely to our equation for efficiency. So efficiency is the useful output energy transfer over the total input energy transfer, or we can do it with power output as well. Okay, so efficiency is this thing that tells us, okay, how much of the energy that I put in is actually useful to me. It's sometimes given as a decimal, sometimes given as a percentage. Okay, never as a fraction. We just don't tend to do that with efficiency. So in an exam, they could ask you to represent it as a decimal or a percentage. Do note that if you are going to be asked to represent it as a percentage, we need to times this by 100. Okay, so do remember that if you're showing efficiency as a percentage. Okay, so a very efficient device wastes very little energy. All the energy that we put in is pretty much going to what we want it to go to. A very inefficient device wastes most of its energy. Okay, so that's how efficiency works. So, okay, we have some unwanted energy that is going to waste. Now, how do we reduce the waste energy? Okay, so how do we make something more efficient? We reduce the amount that is being wasted. Okay, if we're reducing the amount that is getting wasted, we have more to go into what we actually want. So, waste energy usually goes into the surrounding environment and heats it up. That's usually where waste energy goes. So, for example, in a light bulb, it's obviously being lit up, but it's heating up at the same time, and that heat is dissipated into the surrounding environment. Not useful, and is lost as waste. It's hard to get back from the surrounding environment, so we have to prevent it leaving in the first place. Okay, so how do we prevent it leaving in the first place? Well, there's two main ways that we do this. The first is lubrication, and the second is thermal insulation. So let's first of all go through lubrication. Lubrication is what we use to reduce the effect that frictional forces have in heating up, and we're trying to reduce the waste energy as heat. So, as you know, friction between two surfaces can cause heat. Okay, so for example, a car driving along a road, there's going to be friction between the wheels and the road, and therefore heat. Any two surfaces that come into contact and rub against each other heat up. Okay, and that energy is wasted as heat. It's not useful to us. So we need to reduce the frictional forces. The frictional forces is what is causing this heat. Okay, it's causing this heat to be wasted. So we need to reduce it. We need to reduce the effect that friction has on our object. The way that we do this is either by placing rollers or ball bearings between surfaces, but in most cases we use oil. Okay, so we use oil to lubricate surfaces and allow them to slide smoothly over each other. Okay, so oil can be a very useful mechanism that is used for lubrication, and therefore can reduce frictional forces, which reduces the heat that is being made from friction, and therefore reduces the waste energy. Okay. The other one that we have is thermal insulation. So thermal insulation is talked about in terms of your house. Okay, so heating a house wastes energy through windows, doors, and the roof. They're the main places where heat energy gets lost. And this is a real problem because we obviously have to pay for gas and electricity. Okay, and it's not cheap. It can be really expensive. So we want to make the energy as kind of efficient as possible. We want it to be as useful as possible. Remember, the only use that we have is to heat up our house. We don't care about the outdoors. We don't want to heat that up. We just want to heat inside our house. So we want to try and reduce the amount that is getting wasted, the amount that is leaving through the windows, through the doors, through the roof. Okay, so we can do this using carpets and curtains, but that's not so efficient. It doesn't really help that much in reducing the amount of heat energy that leaves the house. Okay, so yes, carpets help in the floors and by the windows, but only if they're shut. And obviously you don't want your curtains to be shut all the time. You do still want to let light in. So what do we do with windows? Well, we have this thing called double glazing. So double glazing is this process that can be applied to your windows. So you can buy double glazing windows, or you can get double glazing done. And these kind of windows are special. So they have 2 panes of glass, so one on the inside and one on the outside. And between that, we have a little pocket of air or a vacuum between the 2 panes of glass. Okay, now that's really useful to us because the air going through there is insulated. Okay, air is a poor conductor. It's the same kind of thing with energy lost through walls, which can be reduced by using cavity wall insulation. Okay, it has just been cut off there, so I'll rewrite it before. Okay, so cavity wall insulation. Okay, so energy lost through walls, how do we reduce that? So we use cavity wall insulation, which is this insulating material that we put between the bricks on the outside of our house and the wall on the inside of our house. So bricks on the outside and the wall on the inside. Between that, we sandwich this insulating material, which can come in lots of different forms, such as foam. We can have something like a fibre in there to really insulate between the outside and the inside. Okay, now this reduces the loss by air circulating inside the cavity. So it reduces the loss by convection. Okay, so that means that the thermal conductivity is reduced. And don't worry about, if you don't know what thermal conductivity means, we're going to go through that in a second, but the thermal conductivity is reduced. Now, thicker walls transfer heat by conduction slower than thin walls. Okay, it makes sense because a thicker wall would not allow heat to pass through as easily as a thinner wall. And that's good for us because remember, we're trying to lose as little heat as possible. So adding a material of low thermal conductivity to these walls on the inside or the outside reduces heat loss. Okay, so if we make those walls thicker, that reduces the thermal conductivity, which is a good thing because we lose less heat. Through the roof, it's a similar way to the walls, and we have loft insulation. So if you've ever been in your loft, you may have this kind of yellow fibery foam, and that is used as insulation to stop heat energy kind of getting through the roof and being lost. Okay, so that is how we can reduce energy losses in lots of different parts of our house, so through the walls, the roof, and the windows. So what is thermal conductivity? Well, thermal conductivity is the measure of a specific material's ability to conduct heat. So it's specific to that material. It never changes for a specific material. Okay, so copper has its own thermal conductivity, water has its own thermal conductivity, and so on and so forth for every single material. So it's the measure of the material's ability to pass heat. A low thermal conductivity means it doesn't pass heat well, and this is good for reducing the waste energy to heat. Okay, so a low thermal conductivity is good if we want to keep heat in. A high thermal conductivity means that it passes heat very easily. So for heaters, that would be a good thing. For ovens, that would be a good thing. But in these scenarios that we've just talked about, we're trying to reduce the loss of heat energy. So we want to have low thermal conductivity. If you were there in the webinar yesterday, you'll remember that we were talking about specific heat capacity. Thermal conductivity and specific heat capacity, although different, are very, very similar. Okay, so specific heat capacity is defined as the amount of heat energy needed to raise the temperature of 1 kilogram of a certain material by 1 degree. Okay, so specific heat capacity is talking about how much energy is required to heat up the material by a specific amount. Thermal conductivity is less specific. It's just really the measure of a material's ability to pass heat through. Okay, so how good of a conductor is it, basically, is all it's talking about. Okay, so there is not an equation for thermal conductivity that you need to know, which is great. You do just need to know how to define it and how to apply it to different situations. So talking about if a material has low conductivity, what does that mean? Is it good? Is it bad? Okay, so no equations for thermal conductivity, unlike specific heat capacity. Okay, so we're moving on to the required practical now. And we're going to investigate the effectiveness of different materials as thermal insulators and the factors that may affect the thermal insulation properties of a material. So this is a required practical for thermal conductivity. Okay, so how are we going to conduct this experiment to find out the aims of the experiment? So measure the rate of cooling of a beaker of hot water. That's really the kind of basis of the method that's going to allow us to find what we want. There's going to be 2 parts to this experiment. We're going to split the experiment down into 2 different parts, 2 different results tables and 2 different graphs. Okay, so it can be a very lengthy experiment, which means that the examiners have lots of scope to ask you questions about it. So you can see the 2 parts of the experiment are here. The first part is investigating how the beaker cools down when insulated with different materials. Okay, so we might try cotton wool, we might try cardboard, we might do one without any insulation. So we're going to be trying different materials. Okay, so we're going to be trying to see how effective it is at keeping the heat in. So we're going to start off with a beaker of water, and it's going to be hot. We're going to take a temperature at the beginning. We're going to leave it for a certain amount of time, and then we're going to come back, having wrapped it in an insulator. If the temperature doesn't change much, we know the insulator's done a good job because it's kept that heat energy in as much as possible. If the temperature has dropped by a lot, however, that's bad, and it's cooled down quickly, so the material that was supposed to be insulating has not done a good job. So that is the first part of the experiment. When insulated with the same material but different thickness is the second part. So for this experiment, we're going to be using only one material, and you can choose. And we're going to be doing 4 different experiments with that material with different differing thicknesses. So you might have 1 layer, 2 layers, 3 layers, 4 layers of that material. Okay, so we can see that we're investigating different factors on the rate of cooling, on how good of an insulator that material is. The factors that we're investigating is what type of material it is and what effect does that have, and how much of the material we use and what effect that has. Now, we know the answers to this experiment, and that's going to be the case in a lot of your required practicals, just by looking at the world around us, right? We know that different materials insulate us better. Sleeping under cardboard is not going to keep us as warm as sleeping under cotton wool, okay? So that's why I say when you do require practicals, just take a step back from the method, from the equipment list, from all the exam questions, from the required practical stigma. Just take a step back and think, okay, if this happened in real life, what would the answers be? What would the physical situation be? Because you don't know it, but you actually are interpreting things physically around you all the time. You're doing science all the time. Okay, so that's why I say just take a step back. Okay, so for this experiment, what equipment do we need? So again, two different types of experiments. The first one is this down here in this circle. The second one is up above. So the equipment that we're going to need is 4 100 centimetre cube beakers, 4 250 centimetre cube beakers, and I'll explain why in a second, 4 thermometers, a kettle to heat the water before we put it in the beaker, a piece of cardboard that we can cut up using scissors, a stopwatch so we can keep it for the same time that every experiment that we do as a control variable. Then we need insulating materials, so newspaper, corrugated cardboard, bubble wrap, polystyrene balls, cotton wool. The materials really depend on obviously your school, what they supply you with, but in an exam, if you are writing about the method and the materials that you might use, they are good ones to write down because they are commonly used. And rubber bands to attach it all together. Okay, so why do we need two types of beakers? Well, as you can see in this diagram here, we have the large beaker outside and the small beaker inside. That just helps with insulation and keeping it all together. Then you can see that we've put a lid on it so that no heat is lost out of the top of the beaker. That's obviously a bad thing. That's, remember, heat lost to the surroundings, waste energy. We stick our thermometer in it and we're going to do 4 different experiments at the same time. So taking the first part of the experiment, which investigates different materials, we're going to have 4 different beakers lined up. With each beaker, we're going to have a different material. Okay, so the material is going to go in here between the large beaker and the small beaker. We might put a piece of cardboard there, we might put some newspaper, we might put some cotton wool, and we might put some bubble wrap. So we have 4 different ones with 4 different thermometers in each. Pour our kettle in, start the stopwatch. Come back 10 minutes later, what temperature has it got to? Whichever has the smallest drop was the best insulator. That's really how it works. Second part of the experiment that we do with different layers of thickness, same thing again, 4 beakers lined up, 1 layer of newspaper on one, 2 layers, 3 layers, 4 layers, okay? And same time, whichever one drops the fastest is the worst insulator. And we will expect to see that the one that has the littlest insulator, the smallest amount of insulation, will drop the fastest. So the results tables that we're going to have is, for the first part of the experiment, the material, so none, bubble wrap, newspaper, tin foil, they can be swapped out for whatever materials you're using. The temperature at the beginning, temperature 3 minutes later, 6 minutes, 9 minutes, 12 minutes, 15 minutes. Remember, you can pick whatever intervals you want, but this is taken from the AQA required practical booklet, so I would definitely go with 3 minute intervals. And that's a good amount of time to really see a temperature change. If you do 1 minute intervals, that's kind of too long. You might only see a difference of 1 degree, which is not really helpful. But obviously we do want to plot it in intervals. We don't just want to take it at the beginning and at the end. We want to see how it's changed. Is it linear? Is it a curved relationship? Okay, so that's really going to be our first part of our experiment table. Second part, same kind of thing, but instead of different materials, different thicknesses, so 0 layers, 2 layers, 4 layers, 6 layers, same time intervals, same temperatures. Then we go on to our graph. So our graph is going to look something like this. We've got 5, so this is for the first part of the experiment, remember, when we have 5 different materials. So you can see the materials are different colours, going from pink, green, teal, purple and orange. So they did their experiment with 5. Obviously, however many materials you use is up to you. Notice that the graph starts at 100 degrees, okay, for every single material. That's because you're putting boiling water in the beaker. It should be at 100 degrees. Then it starts to drop off. With the pink line, you can see that in 20 minutes, it's only dropped by about 60. Yeah, it's gone from 100 to roughly 40. The temperature drop is 60 degrees. However, for the orange material 5, we can see that it's gone from 100 to 10 in the same amount of time. So because it's had a bigger temperature drop, that's kind of showing that it's a bad insulator, right? It didn't keep the heat in very well. So that might be an example of newspaper. Okay, newspaper is a rubbish insulator. It obviously allows heat to get through very, very easily. However, material 1 might be cotton wool. Okay, it's really keeping it warm, keeping it nice and warm, and therefore doesn't drop as much in the same amount of time. You may be asked to interpret one of these graphs, so temperature against time for different materials, but it is unlikely that they will ask you to plot the graph just because it does take up so much time. Obviously still could be a possibility, but rare. Now this graph is for the first part of the experiment where we do it with lots of different materials. However, the second part of the experiment can also be done using the same graph. So instead of different materials for the different colours, it would be different thicknesses. So instead of material 1, you'd have 1 layer. Instead of material 2, you'd have 2 layers, and so on. And what you would see is the same kind of plot. So if it's only 1 layer, it's going to be this orange line. If it's more layers, it's going to be this pink line. Okay, because more layers means better insulation. Okay, so that is the end of the content. I will take some questions now before we move on to example questions. Okay, I'm just going to take a few. So is the energy in chemical store transferred to kinetic energy? Well, the energy in fuel is chemical energy, which does get transferred to kinetic energy in a car or a boat. So yes, that would be an example of an energy transfer from chemical to kinetic. But remember, chemical energy doesn't always need to be transferred to kinetic. It can be transferred to other things as well. So for example, in a battery, that's chemical energy being changed into electrical energy to power the circuit. So just to follow up on that question, you've said the energy in the chemical store in the fuel is transferred to kinetic energy or other energy stores. So chemical the chemical energy of the fuel does get changed into the kinetic energy of the car. And then some of that energy, however, is lost to heating up the engine, which is not useful to us. So there would be some wasteful energy in the form of heat. Okay, that will... Okay, someone said, when we say elastic potential energy, is that the same as elastic energy? Yeah, that's exactly the same thing. When you pay electricity bills, how much of the money is wasted energy? Okay, I don't know the exact figures, but when you pay your electricity bill, the amount of wasted energy is really down to your house design. So if you do have double glazing, then you're going to be more cost efficient than somebody who doesn't have double glazing. If you have loft insulation, if you have wall insulation, you know that your money's going kind of to a good place. So it's going to heat up the house rather than just heat up the outside of the house because you don't have very good insulation. So it depends on the design of your house and what features you have installed in your house to reduce that loss of heat. Okay, that will do for now. We're going to go through a few questions. Okay, so I would like for you guys to do questions 1 and 2 first. So please put your answers on the chat so I can see that you've understood and we can consolidate your learning. So put your answers in the chat for question 1 and 2. What happens whenever energy is transferred between stores? And what is the efficiency percentage of Christmas lights that give out 10 watts of light radiation for an electrical power input of 200 watts? Now remember, the formula is useful over total. So I'll give you 2 minutes to think about the answers to those questions and give you time to kind of put it through the formula. Okay, so what happens whenever energy is transferred between stores? All the energy is not going to go to useful stores. As I said, no energy transfer is 100% efficient. It's not that one. Some of the original energy is dissipated. Yes, some energy will be lost inevitably to wasteful energy sources. All of the energy is dissipated. No, some of it does go to useful sources. Then for the second one, what is the efficiency percentage of Christmas lights that give out 10 watts of light radiation for an electrical power input of 200 watts? So first of all, we need to identify what the useful source of energy is. So Christmas lights, all we want them to do is light up. So the useful energy is the light radiation. So they've given us useful energy, or in this case, useful power. Remember, they can be interchanged. So our useful is 10. Our total then is a total electrical power input of 200 watts. So remember, the equation tells us to do useful over total. So 10 divided by 200 is 1/20. Now, remember that we need to have it as a percentage. So we times by 100. So that we get 100/20. Which equals 5%. Okay. So the answer for the efficiency of the Christmas lights would be 5%. So remember, we're doing 10 divided by 200 and timesing by 100. So useful over total and times by 100 to find out just how much of that energy is going into what we actually want. And you can see that it's only 5% of the power that we put in is actually being used. Okay, so 5% of that 200 watts is going into lighting the Christmas lights. Very, very inefficient. Okay, considering that that's the only purpose of the Christmas lights, only 10 watts of the 200 watts is going into the lights. Where is the other energy going? Well, the rest of the watts, so 190 watts, is being split into other wasteful energy sources. So some is going to be lost as heat. So Christmas lights tend to get very hot. And so a lot of the energy is being wasted as heat. Some of it is being lost in the wires between the bulbs. So it's got a lot of wiring on Christmas lights, which means lots of kind of scope for the energy to be lost. Okay, energy is lost in wires because of the resistance of the wires. Okay, so that's another place where energy can be lost. Okay, so the question underneath that, which of these cannot happen to energy? Energy cannot be stored, energy cannot be dissipated, or energy cannot be created. So that one would be energy cannot be created. Remember, energy cannot be created or destroyed. We'll move on to this one over here. How might a toy car be made more efficient? So how can we make our cars, our toy cars, go faster? Do we push it with greater force, press down on it harder, or add a little oil to the moving parts? So by adding a little bit of oil to the moving parts, we're doing that process of lubrication that we saw earlier. So remember, that process of lubrication is adding oil to the moving parts, the parts that are in contact with the table that the car is being pushed on, and reducing the frictional forces. Okay, so by reducing the frictional forces, we're reducing the energy that is lost to heat because of friction. Okay, so now we have a 30-watt light bulb using 600 joules of electrical energy in a certain period of time. In that time, it produces 450 joules of light energy. The rest of the energy is wasted. So what is the amount of energy wasted? So we're putting in 600 joules of energy, but only 450 of it is useful. So how much is wasted? So this brings us on to another kind of equation, but it's not really a formal equation. It's kind of just a given. So total energy is useful energy plus waste energy. Okay, there's no other kind of secret energies that we haven't talked about. It really is just the total energy that you put in will either be useful or it'll be wasted. Okay, so total energy is 600 joules. So it says that it uses 600 joules of electrical energy. So that's the total energy being put into it. The useful energy is 450 of light. So the waste energy is 600 minus 450, which is 150 joules. Okay, so we can see that the useful is 450, the wasted is 150. So how do we work out the efficiency of this light bulb? So if we remember, the equation for efficiency is useful, which is 450, divided by total, which is 600. When we divide 450 by 600, we get 3/4. Okay, so turning that into a percentage, 3/4 as a percentage is 75%. So we can see that this is pretty efficient as far as light bulbs go. Okay, so now we have a 75% efficient light bulb, so pretty efficient. One thing that I do just want to point out is that useful energy doesn't always need to be just one type of energy. So sometimes appliances have two functions. Okay, so an example would be, so at the start of a race, sometimes they use a pistol to announce the start of the race. Now that pistol fires a flash and a bang. Okay, so the flash can be seen and the bang can be heard. Now that is two uses for one appliance. The kinetic energy being put in by pulling the trigger is going to two useful energies, light and sound. Okay, so that is an example where there can be more than one useful energy. Okay, so I'm going to go through some questions for the last kind of 10 minutes or so. So if you do have any more questions about today's webinar, or indeed any kind of topic from energy that we've covered, as we are getting to the end of energy now, do let me know, so it doesn't necessarily need to be about today's. Someone says, can you give examples of inefficient and efficient devices? Okay, so an example of an inefficient device would be your standard halogen light bulb. Okay, so halogen light bulbs are rubbish. They are very, very inefficient, and they kind of, you can get energy saving light bulbs, but halogen light bulbs, the kind of cheap ones that are used in most houses in everyday life, are pretty cheap and pretty rubbish. They lose a lot of energy to heating up. However, on the flip side of that, we have LED light bulbs. Okay, so some houses have LED light bulbs, and it's a good choice to make to change your halogen light bulbs to LED light bulbs, because although LED light bulbs are more expensive when you first buy them, they last a lot longer and they are a lot more efficient. So all the energy that you put into an LED light bulb pretty much goes to lighting the LED. Not much of it goes to heating up the LED. Okay, which is why it's so good. We're losing less energy as heat so that more energy can be used to light it up. Is low thermal conductivity a white body? Okay, so this is an interesting question if you know what white bodies are. A white body would not necessarily have low thermal conductivity, because white bodies and black bodies are all to do with infrared radiation, and that's not necessarily connected to thermal conductivity. Yeah, so someone put an example of another appliance which has two different useful energies. So TVs give out light and sound, which are obviously both very useful to us. So in that example, the wasted energy would be, again, it heating up. So some TVs, at the back of them, the wires start to heat up. That would be wasted energy, but actually there are two sources of useful energy. What level would energy questions be on AQA Synergy exams? Okay, so if you're sitting the AQA Synergy exam board, everything that I've done is foundation, except the part where I talked about increasing efficiency. So lubrication, thermal insulation, that's higher tier stuff. If energy can't be destroyed, why do we try to save energy? Okay, that's a really good question. So if energy can't be destroyed, what's the point in saving energy? Okay, so yes, energy can't be destroyed, but let's take our example of a light bulb, for example. So we put electrical energy in, and most of that is going to heat energy, which is not useful to us. Some of it goes to useful energy, which is light. Okay, so the reason that we try to save energy is by trying to reduce the amount that goes to waste. Okay, so what we talk about when we say saving energy is trying to reduce the amount that goes to waste and try and save the amount of energy for useful purposes. Saving energy is important because remember, energy is costly. We have to pay for energy in our homes. And we'll talk about this a little bit. Actually, we'll talk about it in tomorrow's webinar when we talk about renewable and non-renewable energy resources. So we really want to try and use as little energy as possible, because to get energy, we have to create it in power stations we're using mostly non-renewable sources, and that's bad. We don't want to be using non-renewable sources because that increases fossil fuels, which leads to global warming. Okay, so we try to save energy mostly because it's costly and ruins the environment if we're using non-renewable sources. Okay, so that's really the main reason. How efficient are light bulbs? It really depends on the light bulb you had. As I said before, halogen light bulbs are not very efficient, but LEDs are much more efficient. And that has come up in GCSE exam papers time and time again. The standard question, which asks you to compare two light bulbs, and I have done a video on it, so you can find it on YouTube. And it basically takes you through the question of comparing two light bulbs to each other. You're given their cost, you're given their useful power output, you're given the total power input, and I think you're given how long they last. So it's a nice little comparison exercise that they get you to do to really look at what is probably the most useful thing that will come out of physics, of you studying physics GCSE, which is this real life application of what light bulb do you need in your house. Okay, what is costing you the most money, what is going to be most efficient for you. So energy is quite a good kind of part of physics which actually helps you to see kind of what the applications are in the real world. So sometimes, and I've certainly experienced this when we're doing our GCSEs, it's very easy to kind of say, I don't see the point in this. I don't see where this applies in the real world at all. How is this going to help me at all? And I can honestly say that this part of physics, this energy part of physics, costs, renewable sources, non-renewable sources, is very important if you become homeowners in the future, at uni, for example, knowing about non-renewable sources, being environmentally aware. So it is a really important part of the GCSE. How efficient are LEDs? LEDs, I think, are like 20 times more efficient than a halogen. Don't quote me on that figure, but they are very, very efficient. And that's because most of the electrical energy that you put in goes to lighting up the room. Okay, so most of that electrical energy goes to lighting up the room. Our money is not being wasted on just heating up the room, which we didn't ask for. Okay, so we have to pay for energy. So we want as much energy as possible to do the things that we want. We have to pay for the energy going into our microwave. So we want as much energy to go into heating up our food than to heat the microwave, which we didn't ask for. Okay, so really just think about it in terms of the function of the appliance, as that can be a really good way to look at it. Okay, so do smart meters drastically increase energy efficiency? Okay, so smart meters are a really good kind of tool for making you aware of how much energy you use. They don't necessarily increase energy efficiency, but they can help you to understand where your kind of energy is going and help you to be more cost effective. But energy efficiency really depends on what kind of bulbs you have, what kind of insulation you have in your house. So really efficiency is kind of down to you to make the correct kind of choices for your house. So if you still have halogen bulbs, that's less efficient and your money is being wasted on heating up the room. Same thing for double glazing windows. If you don't have double glazing windows, you're going to be losing a lot of heat and your money is being wasted in heating up the outside of your house. So it really is just being kind of cost effective and cost aware of where your energy is actually going. The thing with all of this talk about changing your halogens for your LEDs and your windows for double glazing windows is there is initially a high cost. Okay, so LEDs are more expensive than halogens because they are more effective. Double glazing windows is more expensive than normal windows because it's more effective. So although there is a higher initial cost, it's more effective and it's going to save you money in the long run. But some people don't like to kind of make that step, or they don't have the initial funds to put into that, and that's okay. But yeah, it's just all about being energy and cost effective. Okay, so someone said, is it better to get a standing charge or a charge per kilowatt hour for your electricity bill? Okay, again, it really comes down to what kind of bulbs you have. So a charge per kilowatt hour is probably good if you have efficient light bulbs, but a standing charge is probably better if you don't have efficient light bulbs. Yeah, so it really just depends on kind of how your house uses energy. I think that is all the questions and probably a good place to stop. Tomorrow we're going to be covering renewable and non-renewable energy resources and national and global energy. So tomorrow will be a really good one for kind of real life applications.
Amazing. Thank you so much for a great session, Preshayla. And thank you guys for joining us. Just to let you know that if you enjoy the session and you're also looking for some more personalized learning, we offer one-on-one tuition, which you can find out more about on our site. Also, all of our sessions are recorded and on our YouTube channel, so you can rewatch this session, this amazing session, if you need to. Thank you very much, everyone. Have a lovely evening. Bye.
Thank you. Bye.